I'm going to do my talk in English as well, just like the other Julio. This presentation is called Next Generation Debuggers for Reverse Engineering. And its purpose is to show the latest developments in the ERZ project, which is a project from which I'm a member. This presentation was made by many different people, not just me, so I'm going to try to represent them the best as possible. So I didn't do all of the content of this presentation, not just the slides, but I didn't do all the code as well. So I'm going to try to explain the best about it. So this presentation is about the embedded ERZ debugger. Of course, the title is about debugging, but it's not just about the debugger. It's also about the embedded ERZ tracer. There is the reverse engineering language, a language dedicated to reverse engineering. The unification and reconstruction of debugging formats to be used with the embedded debugger. And about the initial features of program analysis inside the ERZ project. So I'm going to talk a little bit about the history of the project first. It started in 2001 as an academic project inside a university in France. It contains more than 10 components now, 10 different components, most of them libraries, but also different applications written on top of those libraries. And it was featured in 2 different articles in the Frac magazine. So, why talk about debugging? What's the problem about the current debuggers? So, for starters, GDB uses an OS level API for debugging. Namely, it uses ptrace to communicate with the process. So, it doesn't work if ptrace is not implemented on the system, or if it was removed for security reasons, for example. So it is also very sensitive to variation of the environment. For example, the linking of dynamic objects in hardening into Is-trace and L-trace, which can be also used for reverse engineering, use ptrace as well. Also, they have very few interaction with the user. It's basically just a command line based application. You just write a line and you go. And none of these frameworks rely on a real language dedicated to reverse engineering. So as I said, the project started in 2001. It started with just one person, which was the creator of the project and still the mentor and main developer. And we made it like that for about 3 years, basically just him developing that. Someone else joined the team to develop libasm, which is this assembly library. And another person developed libdump, which is a library to communicate via network with the debugger and the ERZ framework. And since last year, since about halfway last year, it started as a community project. And so far we have had about 10 different people working in the project. So this is the structure of the modern ERZ project, which started just with the ELF shell, which is the most known application. Before ERZ became the ERZ project, it was basically the ELF shell project. The ELF shell is an application to manipulate binaries. Basically, you can inject code statically and that kind of stuff. So now we also have the embedded debugger, which is a debugger injected inside the process. I'm going to talk about that later. We have the embedded tracer, just like the debugger. It is embedded inside the application, so it's injected inside the binary. We have now kernel shell. It's not completely released yet. It's just very, very new here. The kernel shell is like the elf shell for kernel. So now we are able to instrument the kernel code as well. And now we have Evarista too, which is a program analyzer inside the RZ project. It's something that we are working on very hard now. And all of these 5 applications are built on top of many, many libraries, such as the library librevm, which is the language interpreter for the RZ language. We have libnione, which is a library for fingerprinting and code analysis. We have libaspect, which serves many data structures for the rest of the project. Libasp, as I said, is this assembling library, very important in the low level of the project. A library to use the debugging formats, and finally a library to provide the user interface, which is basically read-line based. This is just a small graphic to show the organization of the project. Here we have all those applications that I mentioned, plus the libraries. So, the RZ contributions are, first, we can debug hardness systems now, because we don't use ptrace, as I mentioned before. So it is compatible with PAX and GRSec, which can disable the ptrace system call. We also have a very effective analysis because we improve the performance of fuzzing, mainly because we run the debugging from inside the process. So there is no context switching. We don't have to communicate with the operating system and with another process. We are inside the same process, so we do memory access directly. We have a reflective framework, which basically means that from inside the framework you can check some structures and you can change them in runtime, so you can modify the framework on the fly. And we have the first reverse engineering language. We are trying to develop a language to program the framework that is completely dedicated to reverse engineering and making the reverse engineering tasks more easy. So this language now it contains hash tables, regular expressions, loops, conditionals, variables, and all the ELF objects, all the information of the ELF format of the binaries are accessible from that language. This is a small example of how the language looks like. Basically, it's just printing the symbols from the symbol table in a binary. So basically, we are loading the binary, which is SSH, and you can see we can access the objects from the ELF format directly, like that 1.sht. So we are accessing the section header table. We have a loop, which is the for each command. That's also another example. Here we are showing the use of hash tables. We are creating a hash table with all those elements, different machines, and we are using again a loop combined with the regular expression matching to print the elements that start with Spark. So we also have many other hash tables which are by default available in the language. Basic blocks, a hash table of functions, You can apply regular expressions on that, just like the other example. And many different hash tables. There is a command just to list them, which is the tables command of everything. So about the debugger itself, as I said, it does not use ptrace. What happens is, using the RZ framework, we can load a binary and we instrument that binary to inject the code of the debugger. So the next time that you run that binary, for example SSH, it's going to start the debugger and not the SSH. So after starting the debugger and all the objects that are needed for the debugger, you can run the SSH process normally. But the debugger is going to be run inside the same address space as the SSH, as the debugger. So that's why we don't need to use ptrace. We don't need to communicate with the operating system. We just do a normal memory access inside the same address space, just like we were part of the process, because we are part of the process. So the debugger has a proof of concept, which is a working proof of concept, a working application developed for Linux on the x86 platform. It is scriptable using the RZ language. It supports debugging of multi-threads right now. And as I said, you don't need to communicate with any kernel code. So you can execute in that kind of hostile environment. There is an environment that you don't have access to the normal resources that debuggers use. There is just a small figure showing how the process works. We have the hooked process right there. The debugger threads communicating with the core debugger. So we have the classic features of debuggers, like breakpoints. We can also do stepping using the seek action system call. And we have this very nice feature, which is allocation proxying. Because when we're talking about running the debugger from inside the process, the biggest problem that you see is that, of course, the debugger is going to change the memory inside the process, because we have to allocate a space for all the objects that the debugger uses. But actually, this is not the case. We have this technique called allocation proxying, that we maintain a separate heap and a separate stack just for the debugger. So when you run the modified binary with the debugger embedded, it's not going to change the memory of the process. So you can be sure that everything that's going on with the memory of the process is just like it's happening, what would be happening if the debugger wasn't there. We have a different heapness and a different stack just for the debugger. So allocation proxying, there is sort of pseudo code showing how it works. Basically, when there is a malloc or any other kind of allocation function called from inside the process, we check from where this request is coming from. So if it's from the debugger, we return a pointer from our heap. Otherwise, we return a pointer from the original heap of the process. We also have a different support for debugging formats. So I'm going to talk a little bit about the debugging formats here. Basically, a debugging format is something that holds information about a program. So it gives names and position of variables, functions, files, and also stores type information to be used with the debugger. Right now, we have many different debugging formats available. we have blocks, we have steps plus, dwarf 2, the GDB format, and etc. And all of those different debugging formats are difficult to manage because we have, for all of them, we have different ways for parsing and for reading the information. And it causes much confusion for debuggers. And it's very hard to implement the support for all those different debugging formats. So what we did is create a unified debugging format to be used with our debugger. We start by parsing the debugging format, and then we transform it to our unified debugging format, and then we clean the code just to contain our format. So we can right now parse at least stubs and dwarf, and if we have information from these two different debugging formats, we can parse both and store a unified information in our debugging format. And every time we want to add support for a new debugging format, we just have to change the backend part. We just have to change how we parse it and how we transform it to our debugging format. The rest of the debugger doesn't have to worry about a new debugging format. We also have developed a tracer, just like LTrace, but it is using the RSD framework, and just like the debugger, it is injected inside the process. So it is also embedded. It's an embedded tracer that runs from inside the same process as the program being traced. We can trace internal and external calls. There is calls to external libraries. We don't use statically stored information about function prototypes. Actually, we use it if this information is available. If it's not, then we have a different way to get the function prototype without the bug information. We use GCC to compile our code and reduce the architecture dependence. As I said, it works with or without the debugging format. I'm going to talk about that a little bit more. And it can recognize strings, pointers, and values. This is how the tracer works, just a small piece of code as an example. Here we are loading the SSH daemon, and we are adding some information about the functions that we want to trace, like packet get string, auth password, sys auth password, and after we tell the tracer that we want to trace these functions, we save a new binary, which is the SSHD2, which is the binary that now contains the code for the tracer to do its job. So, when we run this new binary, the SSHD2, this is the output. It's going to start to run the binary, the original binary, the SSH daemon, and tracing the functions. So here we can see that the functions that we told the tracer to trace are being printed on the screen, like packet get string, auth password, a little bit down there, sys auth password, and we can see how it's getting the values that are being passed during the execution of the program. So we have a username, an hexatone, we have a password, pass1. We are seeing that this information is being passed to the password authorization function, and that this function returns code 0. As I said, with the debugger, as well, the embedded debugger and the embedded tracer, we are improving the performance because we are running from inside the process. We are communicating directly with the process and not with the operating system. So this is a way that we can show how this performance is being improved, both on the debugger and on the tracer. Here we can see the difference in timings for tracing these functions here, open, write, crypt, etc. And you have the different times between the E trace and the L trace in seconds. And we have ratio value on the right. And you can see that the ratio is always bigger for the embedded tracer. That means we are performing better in all cases. In some cases, like the close function, we were performing 5 times better, five times faster. So if you want to write a fuzzer, for example, this kind of performance improvement counts a lot. If you're just doing a normal trace, you're not going to feel the difference because it's just a small fraction of seconds. But if you have a heavyweight debugging, a heavyweight reverse engineering application that's going to be written on top of the RZ framework, so you're going to enjoy that kind of performance improvement. This is the general working of the ELF tracer. We start by looking if we have debugging information or not, so we can try to get the functional prototypes. If we have the debugging information, we just get that from the file. If we don't have, we use some kind of algorithm to dynamically find these functional prototypes. We generate a new binary using GCC. We generate just the code for the tracer. And this code is injected using some of the techniques that were presented in the previous papers from the FRAC articles. As I said, the backend analyzes the function to get analyze the code to get the function prototypes from the debugging format or from the binary directly. We create these proxy functions that are compiled using GCC and then injected into the new binary. This is the first step. As I said, if we have the debugging information, we just extract information about the arguments, for example, the size, the names, the type names, etc. If we don't have this kind of information, we use 2 different approaches for finding the function prototypes inside the binary, which is backward analysis and forward analysis, 2 well-known techniques. After we generate the hook functions, the proxy functions, we compile that using GCC, and we inject that into the binary using the technique of add-rel injection. Basically, we inject that inside the file, and we merge the code sections and the data sections of the original binary and that of the binary that we have just generated. And after that, we have to redirect the code from the original binary so that when you call that function, it actually calls the proxy functions, which is the functions that the tracer uses to do its job, including printing the results on the screen. So we have 2 different techniques to achieve that. One for internal function redirection, when we are tracing functions that are from the original binary file, and one for when we are tracing functions from library calls, external functions. And finally, we have some quick words about the new features of program analysis of the RZ project, which is, it is a new approach that we are taking. And right now, It's just a small application just to build control flow graphs, but we are working on that a lot, and we hope that in the future we're going to have some program analyzers to work on binary files automatically to find bugs, for example, and well, just wait and see. It's going to be really good. So, as I said, we have a graph analyzer. Actually, it's a graph builder to build control flow graphs, which are used by control flow analyzers. Control flow analysis is essential to some kind of program analysis techniques, and it gives information about properties such as reachability or dominance. For example, we want to know whether a function or a block can be reached for the starting point of the program. If this block can't be reached from the starting point, then it can be removed from the program. It is used in compilers for achieving optimization, but also many other kinds of analysis. To build our graph builder, we first have to work on the disassembling library. As I said, libasp is disassembling library from the ERISI project. It is multi-architecture. Right now we support Intel in Spark, and we are also working on support for MIPS, and hopefully in the future other kind of embedded systems architectures. And we have this very cool feature, which is the use of semantic attributes inside the disassembling library. Basically, a semantic attribute is a new kind of information that we give when we are disassembling instruction to tell the upper layers of the ERISI framework what kind of instruction is that. So we have all these different types here. Like we can say whether an instruction is an imperative branch or a conditional branch. If it's a procedure call, an arithmetic instruction, and that kind of stuff. So that the upper layers of the project don't need to worry about the instruction itself, but just its semantics, just what it does. So these attributes works with non-mutually exclusive types, which means that we can annotate instruction to tell it that it is an arithmetic instruction and an instruction that changes flags, for example. So we can have multiple annotations for our same instruction. And as I said, it provides means to blindly analyze instruction. If you think about control flow analysis, for example, you wanna worry about how the blocks jump to each other. So in Intel, for example, you have many different instructions to do this kind of branching. You have jump if above, jump if below, and etc. So when we use semantic annotations, we just have to tell that this instruction is a conditional branch, and that is it. You know, the only information that we need to tell to the graph analyzer. It doesn't have to look for all these different kind of structures. We also have another feature that is provided by lead aspect, which is the use of vectors. Basically, we have all the function pointers for the disassembling routines for all the different instructions. They are stored in vectors, which is kind of tables that are accessible from the ERISI framework in runtime from the language. So when you open a shell, for example, using the ELF shell framework, the ELF shell application inside of the ERISI framework, you can check the values of all these function pointers, and you can change them in runtime if you want. So after you start disassembling a new binary, you can change the way that disassembling routine is going to work for a specific instruction. For example, you want a new disassembly routine for the call instructions. So when we start disassembling, we're going to use the function pointer that you provided. The upper layer of the graph builder, we have libmyoneer, which is the library that actually does the job of building the graph. It can treat both basic blocks or functions, so we can have a graph of the basic blocks of a program or a graph showing the dependencies of the functions. And we use separate representations for these structures, for basic blocks or for functions. But all of them are stored in a generic structure, which is called a container. So these containers can contain any kind of data, basically a void pointer, and they have links to link each other. So what happens is when you're doing a graph using containers, you can have generic routines that can do generic analysis on these graphs, and you don't have to worry about the data you store inside of it. So you can use the same routine for computer reachability in a control flow graph of basic blocks of functions or a data flow graph. You just reuse the routine because you are working on a graph of containers and not a graph of a specific structure. And finally, a small example of how the graph analyzer works right now. If we were building a graph for this program, which is a very simple program, basically it has the main function and two other functions, func1 and func2. Func2 calls func1, and main can call both functions depending on a conditional. So it has an if-else statement. So of course you can see that, but this is the graph generated by the graph builder, and is here basically to show all of these boxes are basic blocks inside the program, and these edges are how the basic blocks interact to each other. So the main function, it starts on that big box on the top, and we have two different edges going out, one with a red color and one with a green color, and that represents the if-else statement that we have on that code. So one of these boxes is calling func1, and another box is called the func2. If we ask to do a graph of func2, that's what we're going to get. Just a simple graph, because func2 is really small. It just calls func1 and returns. And you can see the address of return on that small ellipsis. And that is the graph for func1, which does nothing. It just, when you call func1, it's just going to return. But the nice point here is that you can see that it can return to two different points. So one of them, because func1 can be called from the main function, and the other one because it can be called from func2, as I said. So we have these two different addresses of return explicit in the graph. So what we are trying to do here with the project, which is now a 6-year-old project and quite large, about 100,000 lines of code, is set new foundations for reverse engineering using the debugging of closed source software from an embedded perspective. We are also developing the first language devoted to reverse engineering, just to help reverse engineers to write their applications easily on top of the ARZ framework. And right now we have many concrete applications that are working and can be used by the reverse engineers in the world, such as the embedded tracer and the debugger. In the near future, this is what we would like to do with the RISD framework. We want to compute data flow analysis as well, not just control flow analysis. We are working on program transformation and language built-ins that can do this transformation with just one command, for example, saving, I don't know, many days of development. We are also working on kernel debugging now and kernel tracing. We started with the Kern shell, as I stated before, and we are also going to have in the near future a debugger embedded for the kernel, for the Linux kernel. We are also working on having more portability and supporting many different OSs and architectures, especially embedded architectures such as MIPS and ARM. And we want more integration between the components, such as the tracer and the debugger. We want them to communicate between. So before we start the questions, I'd like to thank you, all of you, for your attention, and especially the guys from the Ekoparty organization. It was really nice that they could bring me here. I'd like to make an open call for new developers. We are always seeking for new developers that are interested in working this new reverse engineering features and techniques. So if you got interested in the project, please come talk to me after the conference. The source code of the current version of the framework is available online for anyone to download in our web CVS. You can see that the version is actually outdated. Now we are working on the 0.8 Alpha 21 version. And please visit our website, which is rcproject.org. And if you have any questions. No questions? Oh.
One question to you. Do you have plans to port this project to Windows platform?
Windows. If we have the intentions to port to Windows, yes. That's not something that we are working on right now, but we are working more on the concepts, on the features of the project itself. So, but after we have that more solid, more stable, it's not going to be very difficult to port to Windows platform. Basically, we just have to change to actually add another component to work with the portable executable binary format, the PE format. So it's not much work, but that's not something that we are working on right now.
Okay. Would it be able to trace function on virtualized applications or just native Linux applications?
I'm sorry, could you repeat?
Will it be able to trace functions on virtualized applications or emulated applications?
Tracing functions in virtualized or emulated applications. Well, I'm not sure. I've never tried that, but I think it's possible. I think it's possible. Any other question? Okay, so thank you very much.